All right, let's share the screen and start this lecture. Here we go. All right. Chapter 26 of Physics 106 for Philadelphia University is Physical Optics, Interference, and Diffraction. This is going to segue us from our topics and conversations on optics in the previous 3 or 4 chapters into a more modern physics approach to end the class. So let's get into it. We're going to talk about superposition interference, dive a bit into Young's two-slit experiment, then talk interference in reflected waves, diffraction, resolution, and finally, diffraction gratings. So, superposition and interference. If two waves occupy the same space, their amplitudes add at each point. We talked about this way at the beginning of the class. This is something very well understood. They may interfere either constructively or destructively. Here are two equations to describe either the destructive or the constructive interference. Note, I will say that this equation is very simplified compared to the rigorous equations on these subjects. This uses M, with 1, 2, 3, negative 1, negative 2, negative 3, which you will know what M is next section. I'm not going to go into it now and spoil that for you, but it's just so that you know these are overly simplified equations. They do the job, but only in a set circumstance. Interference is only really noticeable if the light sources are monochromatic, meaning they're the same wavelength or the same light, and coherent, meaning different sources maintain the same phase relationship over space and time. So you notice interference patterns if, let's say, both lights are red and both lights essentially go through the same medium. If cases 1 and 2 are true, interference can be constructive when the waves are in phase or destructive when they're out of phase. This picture here sort of illuminates that idea. This illustration, interference would be constructive where the path lengths differ by an integral number of the wavelength, and destructive where they differ by a half-odd integral number of the wavelength. What that means is if the waves are lined up such that they constructively interfere, their peaks at the same point, then they are separated by one wavelength of each other, right? If you push that back half a wavelength, so that the peak of one wave and the trough of another wave are set up, then you have destructive interference where the waves cancel. So when I said before that equation is overly simplified, this chapter looks at waves either perfectly constructing or perfectly destructive in their interference. That's it. Obviously, there is more than that conversation, of course, but the equation doesn't do that because you'll get into much more difficult mathematics, and this course is not necessarily built around you having a strong foundation in that math. So, to summarize, the two path lengths, L1 and L2, will interfere constructively or destructively according to this equation. So, if the path lengths are different such that the peaks line up, you have constructive interference, where M would be multiplied by that wavelength lambda. If the peak and trough meet at the same point, you have destructive interference, which is essentially phasing back one of the wavelengths, half a wavelength, which is what the bottom one is. So we can see this idea work in practice with Young's two-slit experiment. This experiment, the original light source needs not to be coherent. It becomes after passing through the first very narrow single slit, which is shown here. So you have a light source down below. It passes through one slit, which only essentially lets, well, we'll get into modern physics now a bit here, which lets essentially, it blocks out all the other light sources, giving you a coherent light source at that first slit. And that first slit then travels into these two, creating this pattern shown on the back wall here. This is a very famous experiment. I'm sure you've heard of it. We'll go deeper into the weird physics side of this in following chapters. If light consists of particles, the final screen should show two thin strips, right? One corresponding to each strip. However, if light is wave, each slit serves the new source of the wavelet as shown, and the final screen will show the effects of the interference. This is Huygens principle shown here, and this is mostly done analogous to a waves breaking in water, right? If you picture those as water waves crashing over some breakers or something like that, they're going to constructively interfere where the wave caps meet each other and produce the diagram as shown before. We'll get more into this in later chapters too. This is a transition from optics to modern. I want to keep stressing that because these things are going to seem complicated, but they're going to fall into place as we continue. As the pattern on the screen shows, which was this pattern back here in the upper right, the light on the screen has alternating light and dark fringes. So the first light refers to like flashlight, and the second light refers to brightness, which is annoying. Corresponding to constructive and destructive interference patterns. The bright fringes are constructively interfering, the dark fringes are destructively interfering. The path difference is given by delta L equals D sine theta. Again, when we show the picture, those will make sense. Therefore, the condition for bright fringes or constructive interference is when the wavelengths are matching each other, where M is equal to a whole integer of that wavelength. So the first time they meet, the second time they meet, the third time they meet, etc., is constructive interference. Dark fringes are where they interfere destructively. And essentially what's going on here is we are showing that the destructive interference is either when the wave hits that M minus 1/2 or the above central bright fringe is when the first trough and peak meet, and the D plus 1/2, which is below, is when the last trough and peak met. I wish they had better diagrams for this stuff. This really goes well with better diagrams. And again, which is why I said these equations are overly simplified, because as we both know, it's not just pure destructive and constructive and destructive interference that goes on with these. There's the entire 180 degrees, 360 degrees of the waveform that can constructively, destructively interfere proportional to how far along in the waveform you are. Hopefully this picture makes a bit more sense given what I've been talking about before. So you have the light. Remember, this light is coherent because that first single slit filtered out all the excess. So you have, when the light enters this slit, it is essentially in time with itself. There's no other light going on around it. And then when it hits this, it breaks sort of like water breaks on a wave. And what you have here on these fringes, these bright and dark fringes, now they use bright, these bright and dark fringes correlate to, as you can see, let's take the central fringe as an example. Notice the central fringe lines up perfectly with where the two waves intersect. Those lines you can think of as the caps, the peaks of the waveform. And when they meet, that's two peaks meeting, giving you a bright fringe in the center like that. However, these waves are going to continue, grow and grow and grow. When they're not meeting, then you have peak trough meeting, which are all the dark fringes shown around it. And then when you get past peak trough, you get to peak again, or trough, giving you again bright fringes. And these peaks and troughs, these dark and light fringes, correspond to how long the wavelength is. So M beam plus 1 corresponds to the length of the actual wavelength, because the wave has to go through its full wavelength to hit another peak, thereby giving you a bright fringe or a dark fringe. The size, and essentially what this is going at is the size of these actual fringes relates to the wavelength itself. So if you send different literally different colors of wave, red, orange, yellow, or G-Bivet, these fringes are going to change in size, but they're not going to change in orientation. You're always going to have bright, dark, bright, dark, bright, dark, bright in the center, surrounded by dark, like that, assuming, as said before, the light is coherent with itself. I hope that makes sense. This is something better done in lab. So if you are watching this and we have a lab, hopefully that'll set it up a bit. I'll probably send a FET lab out to help this stuff cement, because we're starting to leave like the, oh, it's obvious, it makes sense physics. And again, entering that modern physics of, okay, yeah, sure, why not? But we'll get you through it. Don't worry. It's fun stuff. So let's talk interference and reflected waves. Reflected waves interfere due to path length differences, but they can also interfere due to phase changes upon that said reflection. On the left here in A, we have reflection from a lower index of refraction, meaning the wave entered the higher index of refraction, went through it, bounced off the lower index of refraction. When that happens, we do not get a phase change, meaning the wave enters at the top there, bounces back at the bottom, and it's essentially the same wave. It reflects. However, if the wave reflects off of a higher index of refraction, as shown in B on the right here, notice the incident wave is the wave that comes in. When the wave leaves, it is out of phase, such that where the wave entered with a peak and exited with a trough. This is a half wavelength phase change, causing destructive interference. So to recap, there's no phase change when light reflects from a region with a lower index of reflection, and there's a half wavelength phase change, destructive interference, when the light reflects from a region with a higher index of refraction or from a solid surface. There is no phase change for refracted waves. So what this allows us to do is have fun with the light, right? We have this bench thing set up here with reflecting and refracting surfaces, glass of different properties, for example. And we notice that the rays will enter. Some rays will be reflected. Ray 1 is reflected and refracted through. And then ray 2 is a refraction of ray 1's reflection. I hope you can see what's going on there. And what happens is ray 2 will come out at a different wavelength than ray 1. I'm not saying a different wavelength, but a phase changed wavelength, because ray 2 refracted off of a higher index of refraction. There we go. Forgot the word for a second. Sorry. Ray 1 reflected off of the lower index of refraction, the lighter color, and ray 2 reflect off the higher index of refraction, darker color, meaning half wavelength phase change, meaning destructive interference. And the equations on the left there go to show that, where the destructive interference is m plus 1/2, meaning the wave is pushed forward or fallen back by a half of a wavelength. This interference can also occur when light refracts and reflects from both surfaces of a thin film. This accounts for the color we see in oil slicks and soap bubbles, for example. That is that a rainbow on a soap bubble or an oil slick occurs because the light is refracting, and since all those lights are different wavelengths, they're refracting and spreading out. They're not all reflecting back as the same light that came in, white, for example. Now we have not only phase differences and phase changes on reflection, we also must account for the change in wavelengths as light travels through the film. So not only do you have the reflection of ray 1, but the refraction of ray 2 to play around with this as well. Wavelength of light in a medium of index of refraction n is described here, where lambda n is equal to lambda in the vacuum divided by n. Index of refraction is something we've talked about in the previous chapter. Therefore, the condition of destructive interference, where T is the thickness of the film, is given by this. Now, notice this is the condition for destructive interference. So you take your whatever index of refraction you're talking about, n, you then relate that to the thickness of what's refracting and whatever particular wavelength of light, for example, you're talking about here. So lambda vacuum is simply red, I think it's like 580 nanometers, stuff like that, right? Or 440, I can't remember off the top of my head. And then that particular equation will tell you where M is located. Remember, let's go back for a second here. M is these fringes here, where you have light and dark fringes according to constructive and destructive interference. The condition for constructive interference, funny enough, is that same destructive interference equation minus a half. So the rainbow of colors we see in, let's say, a soap bubble or an oil slick is due to the different waves reflecting light differently. Notice here, red has a larger wavelength, so it reflects tighter than blue, which has a shorter wavelength and reflects wider. This difference, when it bounces back, is why you get the rainbow effect, the prisming effect from these bubbles and things of that nature. The phase changes upon reflection depend on the indices of refraction of the film and, of course, the surrounding medium. This is all Snell's law stuff. We're now taking Snell's law conversations, and we are adding constructive and destructive interference patterns to that conversation. DVDs depend on this interference for their functioning. The signal is encoded as essentially tiny bumps on the surface, and the reflected laser beam varies in intensity depending on whether or not it is reflected from a bump or not. Kind of cool. It's also why if you scratch a DVD, it doesn't work, because it doesn't know how to read the data, because it's not reading the data as expected, right? So as the DVD spins around, the laser's staring at it. As soon as the laser finds a difference in the reflection pattern of that laser, as shown in that in the second part here, that tells the DVD essentially to flip from a 1 to a 0, and it allows the DVD's information to be read by the player. So notice here, the bump flies in. The DVD is reading as on, for example, because 1 and 2 are in sync. As soon as the bump hits, the bump is at such a height that it throws off the wavelength destructively, causing a dim, which the DVD player reads as, well, turn it off, and then once you're on top of the bump, things are set the same again. This is sort of the same way that magnetic tape worked for, let's say, VCR players. Just now we're using a laser rather than a head of a magnet. All right, so diffraction. A wave passing through a small opening will diffract. We talked about that at the beginning of this chapter. Again, this is the wave idea, the wave breaking on shore idea, as shown here with water waves, right? This means that after the opening, there are waves traveling in directions other than the direction of the original wave, right? That's what a breaker does. It breaks up the wave, sends out, disperses it. Things happen differently. Diffraction is why we can hear sound even though we're not in a straight line from the source. Sound waves will diffract around doors, corners, other barriers, etc. Again, think of water as your perfect example. If you go to a breaker, go to an inlet to some sort of open water, the water in a stream or the water in a canal is always a lot smoother than the water out in the lake, because the breakers have diffracted and broken the waves so that they're calmer when they enter the canal. The amount of diffraction depends on the wavelength, which is why you can hear on corners but not see around them, right? The sound will bend and reflect and bounce back to, well, in this case, the sound will bend around corners, but light won't, because wavelength differences. Sound is Sound is a different wavelength than light. To investigate the diffraction of light, we consider what happens when light passes through a very narrow slit, as shown here. This figure indicates what we see on the screen is a single slit diffraction pattern. Notice that looks an awful lot like the previous examples we've seen, right? This pattern is due to the difference in path lengths from different parts of the opening. The first dark fringe occurs where W sine theta equals lambda. W, of course, being given by the width, as shown here. Width of the slit times sine of theta, whatever angle is being produced, is equal to lambda. So theta is what we care about in this scenario. Lambda is given by the light. W is given by the slit. The angle at which the light refracts after going through the slit is determined by both the diffraction lighting and whatever light you are giving it. And then the second slit occurs at 2 lambda, and so on and so on and so on, producing this general equation. The width of the slit times the sine of theta equals m, which is a integer, times lambda. Positive negative values of m account for the symmetry of the pattern around the center, right? Diffraction fringes can be observed by holding your finger and thumb very close together. Also helps you not too far away, right? So if you hold your finger and your thumb real close, it kind of looks like the skin is sort of melting together even though you're not touching. That melting together of your fingers is this diffraction we're talking about here. Because the space between them is so tight. I'm doing it right now, looking at my wall here. The space between them is so tight, you get these light and dark patterns emerging. So that's diffraction. Let's talk resolution. Diffraction through a small circular aperture results in a circular pattern of fringes. This limits our ability to distinguish one object from another when they are very close. The location of the first dark fringe is determined by the size of the central spot, as shown here. And Rayleigh's criteria relates the size of the central spot to the limit at which two objects can be distinguished. This is resolution. If the first dark fringe of one circular diffraction pattern passes through the center of a single diffraction pattern, the two sources responsible for the patterns will appear as a single source. They will diffract and come together. The size of the spot increases with wavelength and decreases the size of the aperture. This is, as we'll get into, essentially camera resolution. On the left, there appears to be a single source. On the right, two sources to be clearly resolved. This is a difference in resolution. This has to do, again, as was said before, with the size of the hole things are coming through, as well as the distance between them, the size of the spot and the size of the aperture. Sadly, we're not going too much more deeper into that. If you know much about cameras, this stuff, it's how a camera works. What was talked about here relates, I think, is better understood in the last chapter we had about optics with microscopes, telescopes, things of that nature. Lastly, let's cover diffraction grating. Diffraction grating is a system with a large number of slits that do essentially what we've done previous. As the number of slits grows, the peaks become narrower and more intense. Here you can see a diffraction pattern with 5 slits, where you have a maximums and minimums shown way off in the distance, and that separation is increasing. The position of the peaks are different for the different wavelengths of light, as we've discussed before, and the condition for constructive and destructive grating are shown here down below. Again, given the distance is shown, the theta that comes off from the diffraction, and of course, relating all this to the wavelength of the light itself. There are many ways to construct diffraction gratings. Acoustic optic modulators diffract light from acoustic waves into a crystal. Turning the sound off eliminates the signal, and changing the sound frequency modifies it. So what do you get here? Transducer, right? X-ray diffraction is used to determine crystal structure. The space between crystal planes is close enough that the wavelength of the X-ray allows diffraction patterns to be seen. Essentially, these are all different uses of what we talked about previously, which is the way that light diffracts, the way the light bends around, things of that nature. Gradient spectrometers you allowed to use to understand crystal structures, things of that nature. Could be important for tensile strength, what have you. And diffraction can also be used can be observed upon reflection from narrowly spaced reflective grooves. The most familiar example is the opposite side of a DVD. Butterfly wings do this. Basically, if you see a rainbow effect, if we see a rainbow pattern, that's because light's being diffracted and being released, bent out at different angles, separating it, right? So, a bit of an interesting chapter. They're trying to do a smooth transition here from optics, which is something that, again, you can do in a lab, to modern, which is more difficult, right? But hopefully what I've said here made enough sense. Of course, if you have any questions, feel free to leave them in the comments below. That's going to be very helpful. Shoot me an email or message me or come talk to me about homework assignments that we have on this stuff. It's interesting to understand and realize why things work the way they work. Not only why does like a rainbow work, but why does a DVD have a rainbow on it? Why does an oil slick have these things? Why do all these things exist all over the place, right? Rainbows and bubbles, all the same thing, but they're not. Why they do what they do? Hopefully, I've provided a little bit of understanding behind that. And maybe now you also know why lasers can read things, right? In the next chapters, we're going to dive deeper into the modern side of things, talk about more weird stuff. Hopefully, you're going to enjoy it. Leave a comment below if you want. Talk to your fellow classmates. And talk to you later. Stay safe.